the result of the previous theorem. So now it's proved, we can use it. Right? That's the nature of mathematics, right? It builds on itself. You take earlier proofs to help you prove something further, and you take the result of that proof as input of yet another proof, and so on. Mathematics is cumulative. Alright, so here's a language, call it EQ for equal, or equivalent. So EQTM, and the language elements, so encoding of two Turing machines, M1 and M2, and the condition that this element belongs to this language is that these two machines, well, they're Turing machines, and their corresponding languages are the same. Okay, so L of M1 is the same as L of M2. So now the language of a machine. What is that? I'm trying to remember. I'm getting a bit rusty. I think that means that that the machine recognizes. I'd have to. Could I do it quickly? If I can't do this, we did do this. Which chapter would it be? L of M. Turing machine? Turing machines? I can find it. How do you define L of M? Is it the language recognized or decided by M? Probably. With over 100 pages. I can't find it quickly, I'll give it up. Alright, okay, so another theorem. So theorem 5.4, given this language, and the theorem statement says that this language is also undecidable. We're starting to seriously accumulate results of this type now. More and more languages proven to be undecidable. Okay, usual approach, theory of proof by contradiction. But instead of we're not going to use ATM now. We're going to use EQ. So here's the strategy. So we'll assume the opposite, proof by contradiction. So we'll assume that EQTM is decidable, therefore there'll be a Turing machine that decides it as usual. And the proof strategy, the main idea will be if this is decidable, then this will be decidable. Okay. Now before we had if something or other is decidable, then ATM would be decidable. And that's how we got our contradiction proof. Okay? But instead of having ATM, no, we're just going to have ETM here instead. In fact, it makes life a bit easier than using this here. Right? So now we're going to have a reduction from, instead of ATM to this, we're trying to prove this is undecidable. Okay, so that'll be sort of on your. We're reducing from a problem to a problem, and we assume the from problem is known to be unsolvable, or the equivalent language is undecidable. And before we went from ATM to something, and we're trying to prove that something is undecidable. Well, in this case, instead of using ATM, we're using ETM. So we will reduce this problem to that problem, reduction. Okay. Now we know that that problem is unsolvable, language is undecidable, and therefore we can prove that this is undecidable. Alright, now, okay, so all that's sort of fairly straightforward, I guess. Now we get to the, usually the crunch time. How do you actually prove it? In other words, how do you reduce this to this? Well, this proof should be quite a bit easier, okay? Now, this problem, what is it? Well, I mean the language, the equivalent problem for of the language. What is the equivalent problem that corresponds to this language? Right? Well, that problem is, it's trying to determine whether the language of a Turing machine is empty. Right? You know, it's the language of a Turing machine is empty. That's what this is. Okay, that's the problem corresponding to that. And what's the problem corresponding to this? Well, whether just two Turing machines have the same language. Okay. All right. Now, and here's like the heart of the proof, the main idea. Say one of those languages happens to be empty. Okay. So, well, that means. Now you can see where this is going. This one's much easier. So if one of the languages is empty, just the empty set, then your problem then, it becomes a kind of special case. Well, then you have to show that the other language is also empty. But that's the problem ETM. Now what I've just said is critical. Right? It's the guts of the proof. Right? So I'll say it again. So this problem is to show that the languages of two Turing machines, M1 and M2, are the same language. This equals that. Okay, say one of these languages is the empty set, which is just this. Imagine. Well, that means you have to show that the other language is also empty. Right? But showing that a language of a Turing machine is empty, that's this problem, and that's undecidable. And we just proved that from the previous theorem. Okay. So now, where's the reduction? Where does that come in? Now, so we're reducing this to this. So that's a special case of this when one of the languages is empty. Well, it's next board, so I'll stop there.